Welcome to Section 6-8, Rotary Motion. At the end of this section, we should be able to answer these questions. What is angular velocity? What is linear velocity when working with rotary motion? What is the notation we will use for the various concepts in rotary motion? What is the formula for angular velocity? What is the formula for linear velocity? And how do we use these formulas to analyze the motion of rotating objects? So what's the big deal about rotary motion? Well, let's see what Calvin thinks of it. Here's a nice little strip. Dad says, playing a record? I'll show you something interesting. Compare a point on the label with a point on the record's outer edge. They both make a complete circle in the same amount of time, right? Calvin, yeah. But the point on the record's edge has to make a bigger circle in the same time, so it goes faster. See, the 2 points on one disk move at 2 speeds, even though they both make the same revolutions per minute. Mind blown. Let's clarify some notation before we really start discussing the ideas of rotary motion. So first of all, we're dealing with a circle. So one of the things we're going to need to talk about is its radius. The radius we will simply call r. From the center of rotation to whatever point we're talking about that is demonstrating this rotary motion. A will stand for the arc length, or the distance around the circle that the object is traveling. So the number of units of arc length through which the point moves. Theta, as you can see here, will be the angle through which the point rotates. Usually we'll measure it in radians, but not always. This sign, the V, is going to stand for the linear velocity in distance per unit of time. So that's the linear velocity. This fancy W is also known as an omega, lowercase omega, and that will stand for the angular velocity, which often we measure in radians per unit of time, but it doesn't have to be radians. It's the Greek omega. And then T will stand for the length of time that we're using to measure this rotation through a particular angle. Okay? So now that we have our notation down, let's talk about some of the ideas. The angular velocity of a point on a rotating object is the number of degrees, either in radians or revolutions or so on, could be any of those, through which the point turns per unit of time. So basically how far around a circle, what proportion of a circle have we traveled around? And we'll use again the omega symbol there to discuss angular velocity. The linear velocity of a point on a rotating object is the distance the point travels along the path per unit of time. So not what angle did it cover, but the actual distance around the circumference of its circular path. And we'll use V there. Now notice these are both velocities, so they're both measured in change in something over time. So our omega, or angular velocity, is change in degrees over time, where our linear velocity is simply going to be the arc length over time. So linear velocity and angular velocity are related. If we measure our angle, theta, in radians, and omega is in radians per unit of time, then we can say that our arc length is our radius times the angle measured in radians. We discussed this in an earlier section. Our linear velocity will be our radius times the angular velocity. So linear velocity is radius times angular velocity. Let's take a look at a problem to see how all this works out. We're going to look at a single rotating object, here an old LP or long play record, which many of you may have never actually seen in person. Rotates at 33 1/3 revolutions per minute. we're asked to find the angular velocity in radians per second. So the first thing we want to recognize is this 33 1/3 revolutions per minute. This is some sort of a velocity, and it's discussing revolutions per minute. So revolutions aren't a physical distance, they're a portion of a circle. A full revolution is one entire trip around the circle. So what they're giving us here, as with 33 1/3 revolutions per minute, is an angular velocity. It's just in revolutions per minute instead of radians per second. So we just need to convert the units. This is just like one of those chemistry problems you guys have, or physics problems. So we're going to take our angular velocity, which is 33 1/3 revolutions per minute, and we're going to multiply it by a couple of conversion factors. We need to get rid of the revolutions. So 2 pi radians is the same as 1 revolution. And there's 60 seconds in every minute. And when we multiply these out, you'll see how the revolutions cancel out and the minutes cancel out, and we end up with radians per second. So multiplying through, we end up with 1 1/9 pi, which is approximately 3.49 radians per second. Okay, the second thing we're going to be asked to do is find the angular velocity and linear velocities of the record per second at the point at which the needle is located when it is just starting to play, 14.5 centimeters from the center. So right here is where we're trying to find the angular and linear velocities of the record. Well, the angular velocity, we should recognize this is where Calvin's mind was blown. Both at the center and at the edge, we're still covering a full circle in the same amount of time, no matter how far away we are from the origin. So our angular velocity is the same no matter how far away we are. So our angular velocity is still that 1 1/9 pi radians per second. The linear velocity, here we use the formula up here. Linear velocity is the radius times the angular velocity. So first, all points on the same rotating object have the same angular velocity. So we still have that 1 1/9 pi radians per second. But we're going to use that to find our linear velocity. Linear velocity is the radius times the angular velocity. So our radius was 14.5 centimeters. And we're going to multiply that times the 1 1/9 radians per second. Now, that 14.5 centimeters per radius. One measurement of 14.5 centimeters is the equivalent of one radius. So our radians cancel out, and we end up with centimeters per second. And when we do the multiplication, we should end up with 50.6145, approximately. Finally, they're going to ask us to find the angular velocity and linear velocities of the record per second at the center of the turntable. All right, they keep asking us for the angular velocity at different points on the record, but as we've stated, the angular velocity is the same no matter how far away we are from the center. So even if we're at the center, we're going to have the same angular velocity. So our angular velocity will once again be 1 1/9 pi radians per second. The linear velocity at the center of the table, since our linear velocity is the radius or distance to the point from the center times the angular velocity, if we're at the center, then the distance here in the formula is just 0. So our linear velocity is 0 centimeters per second, because we aren't traveling any physical distance when we're at the center. We're just spinning around in place. Here's another more complicated problem. Here we have connected rotating objects. So this figure we're looking at shows the back wheel of a bicycle, and a small sprocket is connected to the axle of the wheel. this sprocket is connected by a chain to the large sprocket to which our pedals are attached. So there are several rotating objects whose motions are related to each other. So in this example, our cyclist turns the pedals of her bicycle at 8 radians per second. The front sprocket has a diameter of 20 centimeters and is connected by the chain to the back sprocket, which has a diameter of 6 centimeters. The rear wheel has a radius of 35 centimeters and is connected to the back sprocket. So our first question is, what is the angular velocity of the front sprocket? Well, if we look at the diagram, we can see that this front sprocket is connected to the pedals. So if the pedals are turning at 8 radians per second, then any object that's connected and rotating at the same rate will have the same angular velocity. So the pedals in the front sprocket are connected at their axles, so they rotate as one object, which means that their angular velocities will always be the same, 8 radians per second. What is the linear velocity of points on the chain? Okay, well, this chain is going through this, is attached to the front sprocket, and this front sprocket is rotating, and points on the edge of this front sprocket must be traveling just as fast as the chain because they're attached. So if we can find the linear velocity of points on the front sprocket, we can find the linear velocity of points on the chain. Our linear velocity equation, once again, is the radius, or distance from the center, times the angular velocity. Well, our front sprocket, here we go, has a diameter of 10 centimeters. So we need the radius, so half of that, 10 centimeters. And then our angular velocity of 8 radians per second. So first, we want to remember that the linear velocity of the chain is the same as the linear velocity of points on the rim of the front sprocket because they're attached. And then we use our linear velocity equation where our radius, they didn't give us the radius, they gave us the diameter, trying to be tricky, is 10 centimeters. And our angular velocity was 8 radians per second. So we end up with 80 centimeters per second for the linear velocity of the chain. From there, we can ask for the linear velocity of points on the rim of the back sprocket. Well, the rim of the back sprocket is also attached to the chain, so that linear velocity can't change. That chain has to keep moving all the way around at the same linear velocity. So that's the same linear velocity as we just calculated. It's going to be 80 centimeters per second. So now we want to know the angular velocity of the center of the back sprocket. So how fast is this little guy spinning around? Well, here, if we're looking for the angular velocity, we have to recognize that it's the same at every point on the same rotating object, the back wheel. And the radius, again, is half the diameter of the back sprocket. So if we know the linear velocity, then we should be able to figure out the angular velocity. Right? So our back sprocket has a diameter of 6 centimeters again, so we need the radius, which is 3 centimeters. So we're going to put the 3 in there for the radius. And we know the linear velocity, again, was 80 centimeters per second. So we're going to take that 80 centimeters per second and divide it by the 3 centimeter radius. So to solve for W here, we need to take the linear velocity and divide it by the radius. So our linear velocity was 80 centimeters per second. Our radius was 3 centimeters. So we end up with 26 2/3 radians per second for our angular velocity of the back sprocket. whether it's in the center or any other distance away from the center. So after we've gathered that information, we should be able to tell how fast the bicycle is going in kilometers per hour. Well, since the back wheel is attached to the back sprocket with the same axis, then they both have the same angular velocity. That angular velocity was the 26 2/3 radians per second. Right? So we need to take that 26 2/3 radians per second and change it to a linear velocity for the back wheel. So let's first recognize that the speed of the bicycle will be the linear velocity of the rim of the back wheel. From there, we have to find the linear velocity of the back wheel. So again, we resort to V equals R omega. Our omega was the 26 2/3. Our R value is now 35 centimeters. So we start there. We take our 35 centimeters and multiply it by our 26 2/3 radians per second. And that will give us a linear velocity, just not a linear velocity in kilometers per hour. So we need to convert to kilometers per hour from centimeters per second. So we take the seconds and we use the conversion factor of 3,600 seconds per hour so that the seconds cancel out. And then we take our centimeters and use a conversion factor of 1 kilometer per 100,000 centimeters. That's a lot of centimeters. And we will end up with a linear velocity in kilometers per hour of approximately 33.6 kilometers per hour. All right, let's quickly recap. What is angular velocity? Well, angular velocity is the number of degrees or proportion of a circle through which the point turns per unit of time. What is linear velocity when working with rotary motion? Well, linear velocity is the distance the point travels along its circular path per unit of time. How about the notation we will use for these various concepts that we need to discuss rotary motion? Well, we will use R to describe the radius, A to describe the arc length, theta for the angle through which the point rotates, V for linear velocity, lowercase omega, looks like a W, for the angular velocity, and T for time. The formula for angular velocity? Angular velocity, omega, is simply radians per time. Our formula for linear velocity is arc length over time. The relationship between the two is linear velocity equals the radius times the angular velocity. And how do we use these formulas to analyze the motion of rotating objects? Well, we just went through two examples that show you how to work with them. Hopefully, you won't end up like Calvin.